In this lecture, we shall be considering epidemiological statistics. This lecture introduces core principles of epidemiology, defining it as the study of disease distribution and determinants in populations. It contrasts primary, secondary, and tertiary prevention and emphasizes epidemiology's role in clinical practice. Key etiologic models are presented, including the counterfactual paradigm, the sufficient component cost model, and directed acyclic graphs for visualizing causal relationships. We shall distinguish between measures of disease occurrence such as risk and incidence rate, and we will explain methods for their calculation. We will also cover comparative measures like risk ratios, rate ratios, and odds ratios, highlighting their interpretation and appropriate use in different study designs. Yes, we may not like definitions, but sometimes they are necessary. And so we begin by asking, what is epidemiology? Epidemiology is the study of how disease is distributed in populations and the factors that influence or determine this distribution. The premise that underlies epidemiology is that disease, illness, and ill health are not randomly distributed in the human population. We can therefore think of epidemiology as the study of the distribution and determinants of health-related states or events in specified populations, and the application of this study to control of health problems. The objectives of epidemiology are, first of all, to identify the etiology or cause of a disease and the relevant risk factors. Secondly, to determine the extent of disease found in the community. Third, to study the natural history and prognosis of disease. Fourth, to evaluate existing and newly developed preventive and therapeutic measures and modes of healthcare delivery. And fifth, to provide the foundation for developing public health policy. When we talk about prevention, we may classify them as primary, secondary, and tertiary. Primary prevention deals with preventing the initial development of a disease. And examples of primary prevention are immunization and reducing exposure to a risk factor. So, for example, providing clean potable water is a primary preventive measure to prevent diseases like typhoid and cholera. Secondary prevention involves the early detection of existing disease to reduce severity and complications. Examples of that are screening for cancers and other types of diseases. Thus, the key distinction between secondary and primary prevention is that in secondary detection, the disease is already present, and what we are trying to do is to detect it as early as possible in order to treat so as to reduce the severity and complications that may occur. Whereas primary prevention deals with preventing the disease from even developing in the first place. Tertiary prevention deals with reducing the impact of the disease. Thus, the disease has occurred, probably caused some complication, and so what we are now trying to do is to reduce the impact of that disease or complication on the individual. And an example of tertiary prevention is the rehabilitation for patients after stroke. You may well wonder why we have to have this talk or lecture on epidemiology. It is important because epidemiology is critical to clinical practice. The way we practice medicine relies on population concepts. Thus, if we know there's a pandemic going around of, let's say, COVID-19, and the patient presents in our hospital with symptoms and signs suggestive of COVID-19, then we are more likely to make the diagnosis that the patient has COVID-19. So you see that there's this interplay or linkage between epidemiology and clinical practice. And this is illustrated in this cartoon. You've got whatever it is that's going around. Epidemiological reasoning is a multi-step approach. We first determine whether an association exists between an exposure to a factor or a personal characteristic of the individuals and the development of the disease in question. We then derive appropriate inferences about a possible causal relationship from the patterns of the association found. And this is what underpins epidemiological reasoning. And so, to understand causal relations, we have to proceed by a reiterative three-stage process. The first step, or first stage, is to observe the phenomena. The second stage is to create a model to describe or explain observations. And the third step is to use the model to predict future observations. And in using the model, we continue to collect data and continue to observe phenomena. And we tweak or improve the model based on the data we collect and how well it's able to predict future observations. And so you see that it's basically a circular process that reinforces itself. The picture we see on the left is a well-known famous picture. It shows Watson and Crick and their model of the DNA helix. And so, in that seminal paper in which they published, we find one of the most understated conclusions to a biomedical paper ever published. And this is what was written. It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. What models can we use to understand complex phenomena of disease causation? There are several, among which we have the counterfactual paradigm, the sufficient cause model. We also look at concepts of induction and latent periods. We have directed acyclic graphs. Even our study designs are models that can help us to understand complex phenomena of disease causation. And then, of course, statistical probability. What is the counterfactual paradigm? The ideal comparison group will be people with themselves in both the exposed and unexposed state during the same time. What does that mean? It basically means that you compare people with themselves. And you do that in such a way that you compare them at the same time in the exposed state and also in the unexposed state. So imagine, if you will, that perhaps you had a time machine and you had a group of people. So you recruit them and you expose them to the risk factor and follow them through time. And then you take your time machine and you transport this same set of people back to the beginning of your study. And then you follow them through that same period of time in the unexposed state. Of course, since time travel is impossible and we are not God, we know that this comparison is impossible. However, this is a very important paradigm which helps us to think about causation. So every study that we do to evaluate causation is actually based on the counterfactual paradigm. What we try to do is to get as close as we can to the counterfactual paradigm. And this is why the randomized clinical trial is considered to be the gold standard. So direct measurement of an effect is not possible, so we must always depend on what we call substitution steps when estimating effects. And so in a randomized clinical trial, what we have done is to take groups of people that are as similar as possible. So by randomizing them to treatment groups, we basically cancel out differences and have groups that are as similar as possible on the average, and then we follow them through time with one group exposed and the other group not exposed. The validity of an estimate will always depend on the validity of the substitutions. What is the sufficient cause model? Sufficient causes, that is to say causal mechanisms, are groups of component causes that result in disease. So we need to understand that diseases are most often not caused by just one cause, but rather groups of causes. Think about the patient or the individual who has been exposed to Mycobacterium tuberculosis. Is it all individuals who have been exposed to the bacterium that will go on to develop TB? The answer is no. Because we know that several other risk factors or characteristics of the individual would predispose or contribute to the person developing tuberculosis. So we have constellations of phenomena that correspond to individual characteristics. And so looking at our example of the patient exposed to tuberculosis, we may find that factors such as age, immune status, dose of bacteria he was exposed to, and so on and so forth, may be contributory factors in the person developing tuberculosis. So we have different sufficient causes that correspond to different causal mechanisms of the disease. Each sufficient cause is restricted to the minimum number of component causes. Component causes that are members of every sufficient cause are necessary causes. So if we imagine that these three circles before us represent the patient that has been exposed to Mycobacterium tuberculosis, then we know that the red letter A is a necessary cause. Because if the individual did not, or rather was not exposed to Mycobacterium tuberculosis, they would not even develop tuberculosis in the first place. But since each of these three circles represent three different individuals, we may now discover that there are different factors that also are component causes. So the first circle may have a set of component causes that include things like immunosuppression and so on and so forth, right? That has predisposed them to developing tuberculosis. Of course, remember the necessary cause is still Mycobacterium tuberculosis. The second circle may represent another individual who perhaps has some underlying lung tissue disease, right? Which, together with the Mycobacterium tuberculosis, has now predisposed them to also developing tuberculosis, and so on and so forth. So this is the sufficient cause model. It tells us that it's a constellation of component causes which result in the person developing the disease. However, there are also necessary causes which are members of every sufficient cause. So in order for this individual to develop TB, all these causes have to be present. So think of it as factor A, or think of it in this case, you've heard of the aphorism, the last straw that broke the camel's back. So individual has this factor, plus another factor, plus another factor, and yet disease doesn't occur. And then once there are sufficient component causes, disease now becomes apparent. So that's the sufficient cause model that we're talking about. So if disease initiation begins when the sufficient cause is complete, then the induction period is conceptualized only in relation to a specific component cause. So each component cause has a separate induction period, and the last component cause induction period is 0. So we can think of the last component cause as the straw that broke the camel's back. So latent period is the time interval between disease initiation, which occurs at completion of causal mechanisms, and the disease detection. So from the point when the disease is initiated to the point where it is detected is the latent period. And this is what we see in this diagram, which illustrates the etiologic sequence for causal mechanisms A plus B plus C. So A, B, and C are component causes. And so A plus B plus C become the sufficient cause mechanism for disease X. So the first is C. Individual is exposed to C. That causes an induction period for C, because from the point where the person is exposed to C to disease X initiation is the induction period for C. And then we have B, the second component cause is now present. And then finally we have A, which together with B and C now becomes the sufficient cause for the disease to occur. So at the point where A comes in, disease X becomes initiated. And so that's why we say the final component cause has an induction period of 0. And then from the point where the disease is initiated to the point where it is detected is the latent period. So if you think about that discussion about primary prevention, secondary prevention, and tertiary prevention, we can begin to see at which point these things become active. So the induction period from C to disease X initiation is where perhaps we may focus attempts at primary prevention. So we prevent people from being exposed to C, B, and A. But once disease initiation has occurred, and then within the latent period, we are now talking about secondary prevention. So we are screening to be able to detect disease X as early as possible. And so better screening tools will detect it as early or as close to the point of initiation as possible. And then once disease X is now present and detected, we will now be talking about tertiary prevention. So you see how all these concepts tie together and work together. So identification of all the component causes of a sufficient cause is not necessary for prevention. So multiple component causes imply multiple points for preventive interventions. And so we've illustrated this concept already. So conceptualizing multicausality for research purposes. If several phenomena are involved in the development of a specific disease outcome, how do we conceptualize these phenomena in terms of causation for the specific disease outcome? We can do this through the use of graphical models. So path analysis, structural equation modeling, directed acyclic graphs. All these can be used to represent a model of causal order. So what are directed acyclic graphs? These are compact graphs that are constructed by abstracting causal assumptions from descriptions of hypothesized relations among potential study variables that represent exposures, outcomes, and covariates or confounders. Directed acyclic graphs are helpful for recognizing and explaining complex relations, including effect modification and confounding. Graphs must be acyclic. And what do we mean by acyclic? It means that if we move in one direction of the acyclic graph, we should not be able to get back to the starting point. So consider this graphic model of causation for lung cancer. So we have a model which suggests that lung cancer arises from factors such as smoking, lung scarring, radon gas exposure, family history, air pollution, and asbestos exposure. And so this is a directed acyclic graph. Now, assuming we want to do a study that looks at the linkage between coffee and lung cancer. And so this is our hypothesized model that coffee may also result in lung cancer. But this is not complete, because we just saw from the preceding slide that there are other factors that are also associated with lung cancer. So we have smoking. Is there an association between coffee and smoking? That may be possible. It's possible that those who smoke may also take more coffee than those who do not smoke. We do not know. Or it may be vice versa. And then we have all these other components that are present. And then it's possible that coffee ingestion may also be related to family history. So if one grew up in a family where people ingest coffee, then one would probably be more likely to take coffee. So this is an example of what a directed acyclic graph does for us. It helps us to be able to visualize causal relationships. We have comparative measures of disease occurrence. And these measures of disease occurrence are compared either as ratios or differences to derive measures of association or effect estimates that quantify potential causal relations between exposure and disease. The choice of the effect estimate that we use in a study will depend on the following: the study objectives, what kind of outcome is being measured, the type of analysis that we have done, and then confirmation of the data to statistical assumptions. It could also depend on how the investigator wishes to convey the study's findings and interpretation. One of the widely used and readily understood measures of effect or association is risk. This can be interpreted as a probability, and it must be interpreted over a known length of time. The average risk for a group is also referred to as the incidence proportion or cumulative incidence. And how is it calculated? It's calculated as the number of subjects developing disease during a time period divided by the number of subjects followed for the same time period. So it's basically a probability measure. Those who develop the disease over the total number of people that have been followed up for that same time period. In calculating risk, we must consider the induction and latent period for the component cause being studied. And this is difficult to assess over long periods of time because of competing risk and losses to follow up. However, if you are doing mortality studies in which the endpoint you are looking at is mortality, there are no competing risk because the endpoint is pretty much well defined and final. So for that kind of study, the risk may be calculated as number of subjects dying during that time period over the number of subjects followed for that time period. What is incidence rate? Now think about it. When we talk about rate, we're talking about something changing over time. So we use the incidence rate to address the problems of competing risk and follow-up losses. This is a true rate. It's not a proportion or probability. Remember the previous one, which is called the cumulative incidence, or the risk, is a proportion. So, but the incidence rate is expressed as change per unit time. The numerator, which is the number of cases, is the same, but the denominator is the present time experience of the population being followed. So the incidence rate is given to us as the number of subjects developing the disease during a time period divided by the total time experienced for the subjects followed. And so person time experience is the sum of the time that each person in the group was being followed up. Person time experience can stop if the disease occurs, or it can continue for recurrence diseases or outcomes. The time in the denominator should include every moment in which a person being followed up is at risk for an event that would get tallied in the numerator. Mortality rate is an incidence rate where the event being measured is death. Death is an easily measured outcome, but may be caused for different reasons unrelated to the exposure being studied. Incidence rates treat one unit of time as equivalent to another. I'm sure we have come across incidence rates. For example, one of the common ones we use is maternal mortality. Right? So we have maternal mortality rate and we have maternal mortality ratio. Those are two different concepts, but they illustrate the concept of cumulative incidence versus incidence rate. So, again, to compare, the risk takes a range of 0 to 1. It's dimensionless because it's probability. It can be easily interpreted, and it just tells us whether the disease occurred or not. The rate, on the other hand, has an infinite range, and its units are number per time. It requires us to calculate it. But what does it tell us? It tells us when disease occurs. And so the relationship between risk and incidence rate is given to us in this equation. Risk is equal to incidence rate times time. But note that this is only an approximation. The probability of developing a disease cannot be obtained by simply multiplying the average incidence rate by the observation period, because occurrence of disease removes the individuals from the cohort. What are the methods of risk estimation? We have the simple risk, which requires all subjects to be followed for an entire period of time of follow-up. And then we have the density, which requires prior incidence rate estimation. And then we have the life table methods. And then the product limit, the Kaplan-Meier method, which requires knowledge of follow-up time for each subject. Now, these methods help us to estimate cumulative incidence or incidence proportion for disease outcome. They all have advantages, disadvantages, and specific assumptions that underlie them. So for the simple risk, it's appropriate only when there are no or very few withdrawals from observation. So death from competing causes or loss to follow-up. And then when changes make the study subjects no longer at risk for the disease. So this is when we can use the simple risk method. And it's calculated by giving us the number of incident cases of disease observed during the follow-up period over a number of persons at risk at the start of the follow-up period. So this is simply just the cumulative incidence formula that we've been looking at from the beginning. So the validity of this method requires that all subjects be followed up. There are many inherent limitations. So the density method is given to us using this formula. So the risk is given as 1 minus e to the power minus the mean incidence rate times the observation period. So it's the exponentiation of the relation between incidence rate and risk. E, Euler's constant, is the base of the natural logarithm. So the incidence rate and observation period must be expressed in the same units of time. The incidence rate must be the average over the total time period. So how does this work? So we'll look at some worked examples. The average incidence rate for a major coronary event in male smokers between the ages of 40 and 64 is 13 per 1,000 men per year. What is the cumulative incidence over this 25-year period? And so if you look at that, the risk is given to us by 1 minus e to negative 0.013, which you get there from 13 per 1,000. That works out to minus 0.013. That's per year. And then the time period that we're considering is 25 years. So pretty straightforward. And so that gives us a risk of 0.277. However, if we were to just multiply the risk by the number of years, we get 0.325. So you see the problem with this is that they give us two different estimates. But remember, like we said, this is just an approximation. So if incidence rate changes, we can calculate separately for sub-interval of time periods. So that's what we can do using the density method. So look at this graphic. Again, is to try to help us understand these concepts better. So we have 10 subjects followed up over a time period. 5 of them are exposed, 5 of them are unexposed. The red dots represent those who developed the disease. The white dots are those lost to follow-up. And the black dots are those who died. So those particular observations are what are known as censored. Censored because we did not observe the event in the individuals that we followed up. Now, simple risk estimation for the entire cohort is simply 0.4 at 5 years. How do we calculate that? It's easy. We had 4 people who developed the disease, represented by the 4 dots. And the total number of people that we looked at was 10. So 4 over 10 gives us 0.4 at 5 years, isn't it? But what about if we look at the time experience of all these people? So if you were to tally the total number of time spent in the study, it comes to 32 person years. How did we get that? So for example, look at the very first individual, the red dot, had 1 year. The second individual had 4 years. The third individual had 3 years, and so on. So what we do is just add up all the years spent in the study. And so that gives us a combined experience at 5 years of 32 years. So the average incidence rate is 4 cases per 32 person years, which works out to 0.125 per year. So if we now calculated the risk, cumulative incidence, using the density method, we arrive at 0.465. So this gives us a risk. And you can see the difference between the two methods. The simple risk estimate gave us a risk of 0.4, but does not account for person years. Remember, we had 3 individuals who were censored. We simply did not observe the event in these 3 individuals, right? 2 were lost to follow, 1 died. And so, by not accounting for them, we get a biased estimate. So what the density method does for us is that it helps us to account for the present times of even these people who were not present at the end of the study. So how do we compare? So the risk estimate for both exposed and unexposed, just like we said, is 4 at 5 years, isn't it? And this just gives us a risk ratio of 1, right? Because look at the 2 groups. It's just 2 over 5 and 2 over 5. And so if we use the simple risk estimate, it tells us there is no difference between the 2 groups. However, if we look at the combined time experience, we find that the exposed group has 14.5 years and the non-exposed group has 17.5 person years. So it does appear that the exposed group is spending a shorter time being present in the study. So if we are to compare incidence rates, in the exposed group we have 0.13 per year, and in the unexposed group we have 0.114 per year. So it will appear that the unexposed group had a lower incidence rate. So simple risk estimate for both exposed and unexposed tells us there is no difference because the risk ratio is 1. However, if we use the density method, the risk in the exposed becomes 0.498 and the risk in the unexposed is 0.434 and the incidence rate ratio is 1.21, isn't it? And then the cumulative ratio is 1.15. So whether we're using the incidence rate ratio or the cumulative incidence or the risk ratio, we find that the exposed group is at higher risk. So this shows you what can happen using the 2 methods. So ratios measure relative effect of exposure. Rate and risk differences measure absolute effect and are called measures of impact. So the risk difference for this hypothetical cohort study is risk in exposed, which is 0.498 minus the risk in the unexposed, 0.434, which gives us 0.064. And so this is the attributable risk. This is the excess risk that the exposed people are subjected to as a result of being exposed to that factor. And so this assumes there's a causal relationship between exposure and outcome. We have the life table method. And in the life table method, cumulative incidence is estimated directly without having to estimate rates. So how is this done? It's done by categorizing the follow-up period into intervals and then counting the number of new cases and withdrawals within each interval. The risk for getting disease is equal to 1 minus the probability of not getting the disease in the time period. So for example, if there is a 10% risk of disease each year, within a 2-year follow-up period. The cumulative risk is simply 1 minus the probability of developing the disease, of not developing the disease, developing the disease in the first year, times the probability of developing the disease in the second year. And so that gives us 1 minus 0.81, which gives us 0.19. So that's the cumulative incidence over the 2-year period. So this helps us to be able to calculate cumulative incidence. Cumulative incidence, 10% of disease per year for 3 years. It's just an extension of what we just saw in the previous slide. So 1 minus the probability of not developing the disease in the first year, times the probability of not developing the disease in the second year, times the probability of not developing the disease in the third year. And that gives us 1 minus 0.729. So 0.729 is the probability of not having developed the disease at the end of 3 years. We assume that risk is independent from year to year. And so this gives us a risk, cumulative incidence risk of 0.271. So the risk for getting the disease increases every year, but it never gets to 1. The risk for disease can change from interval to interval. So when we talk about epidemiologic measures, we can talk about measures of association, and we can talk about measures of effect. Measures of association reflect the strength or magnitude of the statistical relationship between exposure status and disease occurrence. Measures of effect pertain to measures of association that involve disease incidence that reflect a causal parameter in a particular base population if two exposure groups are comparable. So measures of effect come in when we're comparing groups. So consider this closed cohort. What is the risk ratio? The risk ratio is given to us by dividing the risk in both groups. So in the first group that have been exposed, risk is calculated as those who develop the outcome divided by the total number of people who are exposed, which is A divided by A plus B. The risk in the non-exposed group is given to us by the number of those who develop the outcome divided by all those in the exposed group, in the non-exposed group. So that's C divided by C plus D. And so to get the risk ratio is simply to divide the risk of both. The risk difference is just to subtract the risk in those who have not been exposed from the risk in those who have been exposed. And so that's also what is known as the attributable risk. Remember that. So A over A plus B minus C over C plus D, that gives us the risk difference. So this is what we call a closed cohort. So we have all the people present at the beginning and we follow them all to the end. No loss to follow up. What if it's an open cohort? So we have people dropping out of the study. They are censored. So remember the graphic we saw a few slides back. So in this case, we now look at person time. That's the time experience of the individuals. So in the exposed group, we have a count. And then we have the person time experience. And in the non-exposed group, we also have a count and we also have the person time experience. And so the risk in the exposed group is given to us by the count of individuals, which is A, over the person time experience. So this is an incidence rate. In the non-exposed group is given to us by B over P, PT0. And so again, rate ratio is just to divide those two, right? So A over PT1 divided by B over PT0. The rate difference again is just to subtract the incidence rates. So A over PT1 minus B over PT0. What about a case control study? In this case, we have cases versus non-cases. How do we report that? So we have what is called the exposure odds ratio, and we have the disease odds ratio. They're essentially the same, really. So, but what's an odds ratio? Or rather, what's an odds? We start with what's an odds. Odds is just the probability of an event divided by the probability of the event not occurring. And so, The odds ratio is just given to us by A divided by C over B divided by D. So A over C is simply the odds of having the outcome in cases, while B over D is simply the odds of having the outcome in non-cases. And that's really what it is. Odds of having exposure among the cases. So we know what it is. So these are just the formula. It's just repeating what we just saw in the previous slide. But basically it boils down to AB divided by CD. Right? In a closed cohort, we can calculate odds ratios, just like we do for case control studies. However, what does the odds ratio do for us? It has specific mathematical advantages, but we cannot estimate odds difference. We can calculate odds ratios for case control studies, for observational cohort studies, and for clinical trials using logistic regression. The difficulty or problem with the odds ratio is that it overestimates the true risk ratio, especially when the outcome is common. So bear in mind that the odds ratio can overestimate the true risk ratio. So let's look at this hypothetical closed cohort that we have 2,000 individuals and they're treating them for lung cancer, comparing two treatments, A and B. Those who received treatment A, we had 50 people developing the outcome that we're interested in, yes. And those who received treatment B, we have 20 people developing the outcome that we're interested in. And so, if we calculated the relative risk, we get 2.5, right? Because the risk is given to us by the number of individuals exposed or not exposed over the denominator. So 50 over 1,000, 20 over 1,000. And so, if we calculate the risk, relative risk, we get 2.5. And we can see the confidence intervals go from 1.5 to 4.17. If we calculate the odds ratio, we discover that we have an odds ratio of 2.58. So this illustrates what we just said, that the odds ratio can overestimate the true risk ratio. So we must always bear that in mind. Yes, we use it, but we should bear in mind that it can overestimate. Consider now if the outcome is a bit more common. And the outcome we're talking about is cancer survival at 10 years. If the outcome is a bit more common, the relative risk is still 2.5, as we can see. Because in this case, instead of 50 and 20, we have 500 and 200. So the outcome is much more common. Relative risk is still 2.5, but look at the odds ratio. The odds ratio has ballooned to 4.0. So it's overestimating the relative risk. So bear in mind, if the outcome you're interested in is common, the odds ratio can overestimate the relative risk. And so it's probably better in such instances for us to try to calculate the relative risk so that we do not have a biased estimate of effect. We already mentioned mortality as an outcome. It's useful as a measure of disease frequency if there's a high case fatality rate. If it's relatively easily diagnosed, that's the case or disease in consideration, and then if the disease is rapidly fatal. And then, of course, if it's accurately recorded on the death certificate, and if it's a clinically important outcome. So these are the circumstances under which we might consider mortality data to be a useful measure of disease frequency. Death is easily measured, but it can also be caused for different reasons unrelated to exposure being studied. So that needs to be borne in mind. We know what prevalence is. It measures the disease status rather than the onset. The proportion of people in a population with the disease at one point in time is the prevalence. Do note that the prevalence is affected by both incidence rate and duration of disease. A greater incidence and longer duration result in a higher prevalence. If there's a short duration, right, then prevalence can be lower. And a shorter duration can result from rapid recovery or from death. So bear in mind that prevalence is affected by incidence rate and also duration of disease. The factors that affect prevalence may actually affect duration and not even the incidence. So prevalence is not particularly useful for assessing causal association. And the reason for that is because we cannot establish temporality. So there's temporal ambiguity. We don't know what preceded what. All we are saying is, look, these are the number of people that have this disease at this given point in time. Prevalence is very helpful for assessing disease burden, for medical needs, and for diseases that are of insidious onset. It also provides us a kind of steady state view. So the incidence rate and disease duration are constant and there's no migration. So that's when it provides us with a steady state view of the disease.